ल आज चाहिँ नि थ्योरम छ every principal ideal domain PID R is a unique factorization domain R. Means if any ring is PID, then it is a UFD. Means every principal ideal domain is a unique factorization domain. We have to prove this. The PID भएपछि UFD हुन्छ भन्नको मतलब this means that UFD is bigger set than PID. So let me start it to prove. So we will use let us take R be a PID. Suppose that R is a PID. Then we will show that any element of R, any non-zero non-unit element of R can be shown as the irreducible finite irreducible product of finite irreducible uniquely. यदि युनिक तरिकाले त्यसलाई हामीले फ्याक्टर गर्न सकियो भने त्यो युएफडी भइहाल्छ। त त्यो देखाउनको लागि पहिला हामीले आर बाट यस्तो एउटा एलिमेन्ट लियौं जुन चाहिँ नि जीरो पनि हैन युनिट पनि हैन, then we will show that we can factorize those element uniquely. So let us take A be any non-zero non-unit element of R. We need to show that A can be shown or expressed as factors of finite irreducibles uniquely to show R is UFD. यति देखाएपछि R चाहिँ UFD भइहाल्छ है। So I have taken A as a non-zero non-unit element. Now what is the possibility? If in the case if A is if A can be factorized in अथवा यसरी नभनौं एक लाइन यसलाई यसरी लैजानु भन्दा यसरी लैजाऊ if A is a irreducible means if A itself is irreducible, then our theorem is finished. Then our theorem is done. So let us suppose that A can be shown as the product of B and C. So let us consider that A can be shown as B into C. Now you can see here, if B can be shown as the product of finite irreducible and C can be shown as the finite product of finite irreducible, then again theorem is proved. If both B and C are the products of irreducible elements, then again theorem is proved. Okay. So at least either B or C should not be in the finite cannot be shown in the form of finite product of irreducibles. At least one of B or C. So for convenience अब सजिलोपनको लागि चाहिँ नि let B be not a product of irreducible elements. Suppose that B is not the product of irreducible elements, and again let, and then again let this B can be shown as P into Q, where again if both are the product of irreducibles, then again our theorem is proved. So at least one of them should not be product of irreducibles. Again, by the same manner, again let us consider that P is not a product of irreducible elements. Put that P is not product of irreducible element, and again P will be factorized as S into R, and again S lalini athwa R lalini, and this way we can proceed infinitely. Yeah. So this way, proceeding this way, we can find infinite ascending chain of ideals. Like you can see here that the ideal formed by A is subset of ideal formed by B, which is a subset of ideal formed by P, and so on, so on. This will go infinitely. Yeah.
Infinite.
But actually this is not possible because R is a PID. Infinite ascending ideal chain of ideals. Since R is a PID, so this is not possible unless there is a this is not possible. So our assumption is a contradiction that whatever we assume that A cannot be shown as the product of irreducibles is a contradiction. So our assumption is a contradiction. Hence A can be shown as product of irreducibles. Okay, so the very first part we have completed, that any element A of R PID can be shown as product of irreducibles. Now in the second part we have to show that this product of irreducibles is unique. So in the second part we will show uniqueness. So for uniqueness, let, if possible, let A can be shown as the product of irreducibles P1, P2, P3 dot 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 up to Pn, and again A can also be shown as the product of irreducibles Q1, Q2, Q3
Q1
up to Qm. मानौ यसलाई P सम्म यसरी पनि देखाउन मिल्छ, यसरी पनि देखाउन मिल्छ. Then finally, to show that A is uniquely expressed as the product of irreducibles, we have to show that somehow P1 is associate of sum of Qi's, P2 is the associate of sum of Qi's. Means every element, every irreducibles Pi's and Qi's are associate in some way. Then we can say that the presentation is unique. But one thing more we have to show here, that this element N and M, they should be equal also. Means every irreducible P's are associates of Q's, and the number of irreducibles in Pi's is exactly equal to the number of irreducibles in Q's. दुईटैको नम्बर पनि सेम हुन्छ भन्नु त. We will use here induction theorem. If suppose that N is equal to 1 and M is also equal to 1, then theorem is obviously proved. So there is nothing to prove. So for convenience, let us consider that they both are, or let us consider that N is greater than 1 and M is less than or equal to N. Suppose that the number of elements in Q i's M, it means M, the number of element, is less than the number of Pi's. M is less than N. Now finally I will show that M is equal to N. If I could show that M is equal to N and the irreducibles Pi's are associate of irreducibles Qi's in some order. So let me start it. Since P1, P2, P3 dot dot Pn is equal to Q1, Q2, Q3 equal to Qn, then certainly when this whole item is divided by this whole item, the product is 1. Yeah, this shows that this whole product of Pi's is divided by this whole product. So this implies that Q1, Q2 dot 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 up to Qm can divide to P1, P2. के भयो?
अर्का नेटमा गडबड आइरहेको थियो मेरो.
त्यहाँ आयो भने भन है.
अड्की आइरहेको छ, अड्की आइरहेको छ, त्यही भएर.
ठिकै छ, हेर मैले रेकर्ड पनि गरिरहेको छु. यसलाई चाहिँ तिमीले उसमा पनि हेर्न सक्छौ. So here q1 q2 up to qm, this whole product can divide to this whole product p1 p2 p3 pm, and you know that by this way when p1 p2 p3 pn is divided by q2 q3 q4 qm, the result is q1. It means q1 can divide to this whole item. That this implies that q1 can divide to p1 p2 p3 dot 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 pm, and this implies, since you know every reducibles, since every irreducibles in PID is also a prime element. It means q1 is also a prime element. So by the definition of prime element, if q1 divides whole of these numbers, then q1 should divide one of them, either p1 or p2 or p3. So q1 so q1 divides pi's for some i's. Okay, for some i's q1 will divide to that. So our convenience or आफ्नो सुविधाको लागि, so without loss of generality, let us suppose मानौ p1 sorry उल्टो भयो, q1 divides p1. Suppose that q1 is dividing to p1. Since q1 is dividing to p1, this implies there exists a unit element u1 in R such that when q1 divides p1, p1 can be written as u1 into q1. Okay. So now in the equation number 1 here, suppose that I have written this is the equation number 1, I will substitute the value of p1 over here. Okay, यहाँ राखिदियो भने के आउँछ, the result will be u1 अथवा यसरी भनौं न, when p1 is divided by q1, the result is u1. So it can be written as, the expression is u1 p2 p3 dot 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 p, and that is equal to q2 q3 and dot 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 up to q m. Do you understand this? यहाँ के गरियो भने, if p1 is divided by q1, that can be written as u1, अनि यहाँ u1 आउँछ, बाकी सब यो p2 p3 आउँछ, अनि यहाँ पनि q2 q3 आउँछ हैन. नाउ यति गरिसकेपछि अब यही तरिकाले इन्डक्सन हाइपोथेसिसले के भन्छ भने, नाउ बाइ इन्डक्सन हाइपोथेसिस, अच्छा यो सुरु गर्न भन्दा अगाडि मैले बताइदिउँ एउटा कुरा, q1 is dividing to p1, it means q1 is somehow, q1 is associate of p1. Okay, on the similarly we can show q2 is associate of pi's, q3 is also associate of some of pi's, q4 q5 every qi's is associate of pi's भनेर हामीले यहाँ देखाइसक्यो है, एसोसिएट हुन्छ भनेर. अब इक्वालिटी तिर हामी गइराछौं. त यसरी हामीले भ्यालु रिप्लेस गरियो. नाउ बाइ इन्डक्सन हाइपोथेसिस above factorization, is unique. यो फ्याक्टराइजेसन इन्डक्सन हाइपोथेसिसले भन्छ यो युनिक हुनुपर्छ है। अब यो यदि फ्याक्टराइजेसन युनिक छ भने यसमा भएको PIs को नम्बर हेर त कतिवटा छ, n-1 छ। यसमा भएको नम्बर कतिवटा छ, m-1 छ। So we can conclude and consequently we can see that m-1 is equal to n-1. This implies the value m is equal to n. यो तरिकाले हामीले दुईटैमा इक्वल संख्या छ भनेर देखाइयो। Since m is equal to n and every PI, each PI भनौं, each PI is an associate of some QI, so we say A can be shown as product of irreducibles uniquely. यो युनिक तरिकाले यसलाई irreducible देखाइयो। Hence R is a unique factorization domain. On this way we have solved our theorem.